Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're tackling a problem around the first law of thermodynamics. We have argon, so we have an ideal gas, and this is a polytropic process. So that's where we are in the realm of thermodynamics. The problem statement reads 4.62. Argon is compressed in a polytropic process with N equals 1.2 from 120 kilopascals and 10 degrees Celsius to 800 kilopascals in a piston-cylinder device. Determine the work done and the heat transferred during this compression process. So lots of good information in the beginning, right? First and foremost, argon, right? So argon, bells go out, flags go up, ideal gas. When you think about ideal gas, we're automatically thinking about ideal gas law. That's what it means to be an ideal gas, right? So pressure times volume equals mass or number of moles, depending on the unit you're using for the ideal gas constant, and temperature. Temperature always in Kelvin, right? First thing to note. Then we're compressing our gas. So what does that mean? It means that I am taking this piston cylinder device and I'm pushing down on it, right? So I'm doing work to my system. I'm putting energy into my system in the form of work. Then next up, polytropic process. What does that mean? Well, that's a definition. By definition, it means that it's a constant. The pressure times my volume to an exponent is going to be a constant. Okay? By definition, that's what a polytropic process means. And you'll see that this image actually reminds you of that in case you forgot, right? This is what a test or an exam, something like that, and you forgot about it, the image actually reminds you that that's the case of the polytropic process. And the N is 1.2, so what that's saying is that this guy here is 1.2, right? So this guy here is 1.2. So N equals 1.2. Okay, so whatever pressure I am, so P1 times V1 to that 1.2 will be equal to P2 V2 to the 1.2, which is equal to P3. And regardless of the state we're in, as long as it's a polytropic transformation, it's always going to be that case there. We're going from 120 to 800. We have the temperature of the first state. We are to determine the work. So we want to know that work there that I drew in the image and the heat transferred during this process. Okay, so another good hint here out of this image is that heat is going away from the argon. It's being expelled, put it that way, by the argon. We can be sure of that when we do our analysis. But let's think about this from a first law perspective. I'm going to put here the internal energy. And at this point in time, I'm not sure whether we're going to be going from a higher state of energy to a lower state of energy, like so, or whether we're going to be going from a lower state of energy to a higher state of energy, like so. If this is the case, first possibility is the case, then we know we have our work going in. From the start, we knew that. And know that we have the internal energy decreasing whilst we have energy going in. So for that to happen, we need necessarily to have heat going away from my system. Okay? Over here, if it's increasing, then we also obviously know that work is going in. We knew that from the start. But here I have two options, right? Either, this work is sufficient to be able to increase this internal energy, or I need a little extra boost of heat. So it can go like so, or it can go like so. How to know this? Well, we're going to need to find out the amount of work that we have, right? Because if we have, for instance, just for the sake of argument, if this is 100, okay, and we know that our internal energy increased by 50, okay, that means I need to expel another 50 joules of energy out of the system. So this has to be the case right here, right? So there's 50 coming out too, right? However, if this is 100 and this increase in energy here is, for instance, 200, right? Then I necessarily need heat to be going in, right? Because I need the 100 from the work plus 100 from heat. That's what the first law tells us, right? At this point in time, I'm not sure what's going on. I need to find out more information. So what I'm going to do is I'm going to do my two states, all right? My two states. State 1, and here in state 1, I'm going to have a pressure of, what was it, 120? Yeah, 120, and 10 degrees Celsius. So 120, let's put it here. So this is argon both. There's no mass entering or leaving. This is 120 kilopascals, and this is 10 degrees Celsius. I'm going to go ahead and do 283 Kelvin, because whenever it's like ideal gas, we're going to be working with Kelvin, right? So 283 Kelvin, which is the same thing as 10 degrees Celsius. And then on state 2, all I know is that this is 800 kilopascals. Okay, and obviously I know this is a polytropic process. No mass was gained or lost. So, what's the game plan here? We need one extra bit of information for the second state to be able to define it, right? We know that no mass is leaving or entering, so I can say that P1 V1 over T1 has to be equal to P2 V2 over T2. Okay, so but we still have one, we're still missing one unknown to be able to use this equation. So what I'm going to do is I'm going to use, my game plan is, first I'm going to use the fact that this is a polytropic process to be able to find what is my V2, okay, because I can relate the pressure and the volume. Okay, so I'll find V2. With that, I'll compute what is my T2 using the ideal gas equation, okay? So use that to find out what's my T2. Once I have T2, what I can do is then I can find what is my internal energy, right? Because I can relate this as an ideal gas, so I can use the C sub V to be able to find what's the difference in internal energy from 1 to 2. And if I have that, then I can apply the first law of thermodynamics to be able to calculate the heat. No, I can't. I still need to find out what is the work. Work being done by the piston is going to be, so I'm going to need an extra step here. Where can I find this? Let's do this. So this is 5, and then we're going to need to calculate work here. And I'm going to calculate work by doing the integral of P dV, okay? By definition. Note that in this case here, it's going to be a special case because P times V is a polytropic one. So it's, a special case within general theory. If you memorize that, you can use straight off the equation. Let's do it from scratch here, okay? So first things first, let's find out what is my V2, right? What is V2? So for V2, I'm going to use the fact that this is a polytropic transformation. So I'm going to say P1 times V1 to the 1.2 has to be equal to P2 times V2 to the 1.2. In this case, P1 is 120, V1 to the 1.2, and then this guy here is 800, V2 to the 1.2. So note that what I'm going to get out of this is a relationship between V1 and V2. I'm not going to get actual values, but I'm going to get a relationship. So then I can apply this guy here and find out what's the temperature, right? I don't need to know what the actual volume is. As long as I know what's the relationship between V1 and V2, I'm good to go. Okay, so in this case here, I'm going to say that my V1 to the 1.2 is simply put my 800 divided by my 120 times my V2 to the 1.2, which means that if I take the square, it's not even the square, it's the root of 1.2, right? So if I take a root of 1.2, 1.2, like this, V1 to the 1.2, and I also take the 1.2 root of 800, 120, V2, 1.2, I can find out what is the relationship between the two of them. And what I get out of this is that V1 is equal to about 4.86 V2. Okay, so now V1 is greater than V2, right? V1 is greater than V2. This is being compressed, so it makes absolute sense that this is the case, right? We expect V2 to be smaller than V1 as we're compressing the Argon. Cool, so how can I apply this now? So note that we had a relationship that said P1 V1 is over T1 is equal to P2 V2 over T2, right? So that means that my T2, if I want to solve for T2, all I need to do is P2 V2 times T1 divided by P1 V1. Okay, and note that this relationship here now we now have. So I can go ahead and say where I have V1, what I'm going to say is, let me sub that in. So where I have P2 is 800, my V1 is 120. Where I have V2, I'm going to go ahead and say this is 4.86 V1 divided by V1 times T1. So note the only unknown that I have now is T2, right? Because this says, as we know, 283. Okay, unit-wise, what's happening here is that we have kilopascals on the pressure on both ends. Then we have the same units for volume, whatever that is. Okay, I'm going to say it's going to be meters cubed, but it can be whatever. And then we have Kelvin there. So these guys all go away, and we're left with Kelvin for the temperature. Okay, so T2, do this math here, and we get that out of this, that T2 is 387.7. 387.7 Kelvin. Okay, so now note that I have something very important. Now I know what's happening with my temperature, and because I know my internal energy, is a function of my temperature, I can tell you for sure whether it's increasing or decreasing. Our original temperature is 283, our new temperature is 387. So my internal energy is increasing. So let's go back to our drawing, our analysis. What is it? Here it is. Okay, so this is not the case. I'm not decreasing my internal energy. I am increasing it. Okay, by how much? Well, I don't know. I'm going to have to check, find out by how much I'm increasing it to then be able to tell whether my heat is entering or leaving. All right, the drawing, right, implies that it's leaving, but we can be sure by doing our analysis. All right, so next step up is, okay, let's calculate how much work is actually being done here. And then once we do that, we can calculate how much internal energy is increasing. And then with that, we can find out what is the heat going in or out of our system. Okay, work. I'm doing the integral of P dV as I'm going from state 1 to state 2. However, I know that P, I put it here in the corner, so I know that P times V to the N is a constant, right? So what I can do now is I can say, okay, if this is the case, then I'm going to divide both sides by the pressure, and I'm going to have this, right? So that V to the N is a constant. Or what I can do even better if I want is I can do the opposite. I can leave the P here and I say this is V to the N. So the pressure is a constant divided by V to the N. And I can substitute where I have pressure here. I'm going to put pressure here. And what I'm going to be left with is this relationship here, V2, constant dV divided by V to the N. Okay, so now we have an integral of the natural log. And we can sub that in. Note that the constant can leave this integral, so it's going to be work will be that constant. And then we have the natural log of, we do this once again slowly. So we have the integral of V1 to V2 of, yeah, there you go, dV, the V to the, so this is the equivalent of being, V to the minus N. So when we integrate this, we're actually going to have that in backwards. But one thing I want to do before integrating, the last thing I want to do before integrating is I want to substitute this guy back. That's what I was looking for. Okay, and I'm going to use obviously the same relationship here, right? So what is the constant? Well, it's just P V N, right? So this is just P V to the N integral of V1 V2 dV divided by V to the N. Okay, now we're good to go. So there won't be any natural log whatsoever in this case here. Okay, we're going to have V to the minus N, and I'm going to sum one up here, and I'm going to divide the whole thing by this, and that's going to be my integration. So this is equal to P to the V to the N times my V minus N plus 1 divided by minus N plus 1 as we go from V1 to V2. Okay, beautiful. So to make a long story short, my work in this case here will be P to V2 minus P1 V1 divided by 1 minus N. Whew, nice. Okay, cool. So, well, obviously, you substitute your V1 here, you substitute your V2 there, you make one minus the other, and here you can choose whether you want to do P1 V1 or P2 V2. That's how you get up with these guys here, right? Beautiful. So now we can say my work's going to be 800 times V2 minus 120 V1 divided by 1 minus 1.2. Okay, we still don't know what the volume is. We really haven't figured that out. Right? But we do know the relationship between the two volumes. And with that, we can either calculate the volume if you want to and solve for the volume, or what we can do is substitute where we have volume by the first law of thermodynamics. Okay, so that's what I'm going to do. So let's just do where we have V2. I'm going to go ahead and say P2 equals M R T2. So V2 equals M R T2 divided by P2. And the same is going to be true for P1. Excuse me, V1. Okay, so this is 800 times M R T2 divided by P2 minus 120 M R T1 divided by P1, and this whole thing is divided by negative 0.2. What happens here? This guy are the same. Note that the mass and the R's are the same for both situations. It doesn't matter, it doesn't change. And what I'm going to do, the next trick I'm going to apply here is, let me just put these guys in evidence. This is mass times R of T2 minus T1 divided by 0.2. And the next trick I'm going to apply here is the following. I don't have the mass, but I can divide everything by the mass. So instead of getting my answer in joules, I'm going to get in joules per kilogram, right? So this is going to be work over mass will be equal to R T2 minus T1 divided by 0.2. Okay, so now we just need the R, ideal gas for argon, ideal gas constant for argon. We have the temperatures, and we can find what's the work. So where's my table? Here's my table. For argon, using this book here, there's no specific table for argon. We can only grab it at 300, so there will be some error associated with that calculation there. So I'm looking for my constant. That's going to be 0.2081. So this is 0.2081, 387.7 minus 283 divided by 0.2. Okay, so the work over mass is 108.9 kilojoules per kilograms.